Question 4 from Section 1 of the 2022 National 5 Physics exam from the SQA. A student is investigating the motion of a water rocket. There's the ground, there's an air pump, there's water, and you pump the air into the vessel, the bottle. The pressure builds up and it pushes out the water, and the bottle launches into the air. Now, the rocket launches because of what reasons? You're getting a lot of sentences there, but the key thing to remember here is that you have to have, if you have an action force, you're going to have a reaction force, commonly called a Newton pair. So a simplified diagram of what's happening looks like this. You see, the rocket will push the water downwards, and the water will push the rocket back upwards. There's the two equal and opposite reaction forces, a Newton pairs. So we've got to seek the sentence out which comes very similar to that the rocket pushes the water down and the water pushes the rocket back up. So statement A, the rocket pushes down on the ground, is false because it's not pushing down on the ground at all. It's pushing down on the water, so we can rule that one out. That's out. The rocket pushes down on the water and the water provides a reaction force pushing up on the rocket. Well, that's very similar to what we've got in our diagram there. C, the water pushes down on the ground. Well, once again, it's not pushing down the ground, it's pushing the water. And D, the force applied by the water on the ground is greater than the weight of the rocket, producing an unbalanced upward force. Sounds good, but not really. You're looking for an action force and a reaction force. We'll rule that one out. E, the weight of the rocket decreases as the water is pushed out. That's true, and producing an unbalanced upward force. Yeah, but it's not explaining how the rocket launches in the first place. We rule that one out. So our final answer is going to be 4B, because we've got to look for a Newton reaction force and action and reaction force pair. The rocket pushes the water and the water pushes back on the rocket, and therefore the rocket will rise up into the air. So the answer is B. Question 5 from the 2022 National 5 Physics exam from the SQA, and it's from Section 1. A ball of mass 0.25 kilograms is released from a height of 6 metres above the ground. We can see the picture there. It falls down a bit, and in a snapshot we've got a snap of the ball just 4 metres above the ground. And we asked to find which row in the table shows the change in gravitational potential energy and the kinetic energy of the ball when it is a height of 4 metres above the ground. Now be very careful here. It's asking you for the change in gravitational potential energy and the value of the kinetic energy at a height of 4 metres above the ground. Let's start at the very top, and we can work out the potential energy of the ball. EP is going to equal to mgh. And that's going to equal to the mass of the ball, which is 0.25, multiplied by 9.8 and multiplied by the height, which is 6 metres. So at the very top, the potential energy is going to give you a value of 14.7 joules. So that's the potential energy at the top. Now the kinetic energy at the top is going to be equal to 0 because it's not moving. So that's the story so far. Potential energy 14.7 joules, kinetic energy 0 at the top. Now 4 metres down, we do the same calculation again. We go EP is going to be 4 metres above the ground, so it's going to be 0.25 multiplied by 9.8 and then multiplied by the height it's up, so it's going to be up 4 metres. And that's going to give you a value of 9.8 joules if you do that in your calculator. So what's the story so far then? The story is at the top we're going to have potential energy equal to 14.7 joules, and the kinetic energy is going to be equal to 0. Now at the height of 4 metres, the potential energy is going to be equal to, we've just worked it out, 9.8 joules. And what will be the value of the kinetic energy? Well, in this case you can see that the potential energy has lost some of its potential energy by falling, and that loss of potential energy must be put into kinetic energy. So what's the change in the potential energy? Well, the change in potential energy, we'll just say delta EP, that means change in potential energy, is going to be 14.7 take away 9.8. So that's going to give you a value of 4.9 joules. So here comes the real answer here then. What's happened is that the ball has lost 4.9 joules of potential energy. That's the change in potential energy, 4.9 joules. Where is that energy gone to? It's gone into kinetic energy. So the kinetic energy is 4.9 joules. So we're looking for a place in that, a row in that table where we have the change in potential energy is 4.9, so it could be that one or it could be that one. But the kinetic energy is 4.9 joules because the change in potential energy has gone into the kinetic energy of the ball. So we're looking for 4.9 and 4.9. So the answer is going to be B for this one. Question 6 from the 2022 National 5 Physics Examination from the SQA Section 1. Astronauts orbiting in the International Space Station experience weightlessness. A group of students make the following statements to explain weightlessness in the orbiting space station. 1. The gravitational field strength inside the space station is 0. Statement 2. The space station and astronaut are both accelerating at the same rate towards the Earth. And Statement 3. Forces acting on the astronauts are balanced. Well, let's take a look at the astronaut and the spacecraft falling towards the Earth, because that's really what's happening. Even though it's going in a circular motion, it's really falling towards the Earth, and it's falling towards the Earth because it's accelerating towards the Earth because the Earth is pulling down with the force of gravity. So in this situation we have got the spacecraft is being pulled down towards the Earth, is accelerating towards the Earth, but the astronaut himself is accelerating towards the Earth. So the result of that is that there's going to be no reaction force from the floor because both things are falling at the same rate, accelerating at the same rate towards the centre of the Earth. Even though they're going in a circle, remember from our projectile studies you can separate the motions. We'll neglect the constant motion round the Earth and just think about the spacecraft falling straight down towards the Earth. So let's take a look at these statements. Statement 1, the gravitational field strength inside the space station is 0. Well, that's going to be false because we do know that gravity extends far out into space. We know that because we see the moon orbiting the Earth. So the moon is held by the gravitational field strength of the Earth. So gravity reaches right out into space. So it will reach right out into that spacecraft as well. So statement 1 is wrong. The space station astronauts are both accelerating at the same rate towards the Earth. That's what we've got here. The spacecraft is falling down towards the Earth, accelerating down towards the Earth, but so is the astronaut. They're accelerating at the same rate. Therefore, they'll not experience the push of the floor acting on them, and that gives you the perception of weight. So in this situation, statement 2 is going to be correct. What about statement 3? It says the forces acting on the astronauts are balanced. Well, this is not the case because the force acting on the astronaut and on the spaceship is accelerating downwards towards the Earth, and the only way that can happen is you have an unbalanced force acting on them, and that's due to the force of gravity pulling them down towards the centre of the Earth. So the forces are not balanced. So what we have got here is an answer, and it's going to be 6, 2. So we're only looking for statement 2, and that's going to be statement B. So the answer to question 6 is B. Here's the proper explanation for weightlessness when we look at the higher version of it. Let's imagine an astronaut is in a tin can and he's standing in that tin can. What are the forces acting on that astronaut if he's not accelerating or he's moving with constant velocity? Well, if he's not accelerating, then we know that the weight acting downwards must be balanced by some other force which comes from the floor. It's the reaction force due to the floor. So your weight pushes down, the reaction force is really the force pushing from the floor, because the floor is very much like, if you think about it, standing on a trampoline. The trampoline sinks down, and the elasticity of the material of the trampoline, it stretches to a maximum and providing an up force to stop you from actually falling through the trampoline. So it's the same with an astronaut standing on the floor of a tin can. His weight is acting downwards, but stopping him from falling through the floor is the reaction force due to the floor, and that's the reaction force R. Now, If in a situation you're not accelerating, you're going at a constant velocity or being stationary, then it's pretty obvious there that both of these forces must be the same. So the reaction force is actually equal to mg. And it's the reaction force R which gives you the reading on a scale which registers your weight. So this particular case, when the spacecraft is not accelerating, the reaction force is going to give you the value of the weight on the scale, which is going to be just simply mg, the weight of the astronaut. But things get different when it starts to accelerate. So if we bring in acceleration in, then we have got an unbalanced force situation. An unbalanced force situation means we have to find out what the unbalanced force is. Now, if we take things going down the way as positive then we can see that the resultant forces are going to be the following. The weight acting down the way we'll call W. We will take away R, which is pointing up the way, because weight, well, everything pointing down the way is positive in this situation. And that's going to equal to MA, which is going to be acting downwards, the unbalanced force, which is MA. Now, if we rearrange this and take the R reaction force over to the other side and take the MA over this side, we're going to get R, the reaction force, is going to equal to the weight of the person, take away the unbalanced force MA. But we know that reaction force equals mg, and it's going to be minus ma. Now we'll stop there and take a breath and look at that. That reaction force R is in fact the weight of the person on the scales, the reading on the scales. So as long as you're not accelerating, you have R equal to mg. But if you start to accelerate downwards, then you see your reaction force is going to become less. You become weightless. And what's more, if you accelerate downwards with the value of g, look what happens. mg minus mg is equal to 0. And that means there's going to be no reaction force from the floor. So in essence, it means that you're weightless, because the reading on the scale would read 0, and therefore you'd be weightless. And that's why the astronauts appear to float about. It's not really that. It's because they, the astronaut, and the spacecraft itself are both accelerating downwards together, and that reaction force from the floor, which gives you the sensation of weight, disappears and leaves you with weightlessness. I hope that helped. That's you a peek into the higher.